Okay, so welcome everybody to the second week's track of somewhat more applied practical sessions. And it's my great pleasure to have Markus Weimer here. He is at Microsoft, principal research scientist there well, the abbreviation is CISL, and I think I'm going to butcher it, somewhat Cloud Information Services Lab. Okay, good. So, in any case, he's going to talk about Reef, and basically that's a alternative way of, performing big data analysis, and he's going to tell you all about that during the week. Okay, Markus, take it away.
Thank you. Thanks for coming. I want to start with, first of all, thanking you for showing up and for Alex and Zico and the organizers to invite me, but also to the Reef team back at Microsoft, two of which are here. Sergey and Yingda have been here last week as an attendee. They will help me out during the lecture, and I will ask them to identify themselves once we actually need them. Shravan, who's probably watching, still hard at work coding the stuff up that you will look at on Wednesday. So great thanks to him. This tutorial will be hands-on keyboard beginning on Tuesday. So on Tuesday, please bring a laptop, bring a charger, because we will compile code, and even though Intel claims otherwise, Haswell doesn't help with compiling code on battery. The whole tutorial will be super pedestrian in terms of the kind of machine learning we will do. The most advanced algorithm you will see is batch gradient descent with line search. It will be fairly advanced on the systems side. So this is kind of the exact mirror image of all the other tutorials that happen here in the morning and before this. And that's why I ask you to ask questions early and ask them often. Because I don't really know what your background is, and it's really tricky for me to judge that by just looking at you while you're rightfully staring at your laptop. So please ask questions early and ask them often. Okay, so I entitled this Towards Resource-Aware Distributed Machine Learning. Towards on paper titles and tutorial titles always means that we don't quite know yet how to do this. Right? That's just the honest answer. And one of the more selfish goals of me being here this week is maybe some of you can help us figure it out for real. Right? So I will mostly talk about open problems towards the end of the session, and maybe one or two of you will find those interesting enough to actually start working on them. But before asking that question, we have another question, and that is, why should I even care about distributed machine learning? Right? Machines are getting bigger, you can stick 4 GPUs into a single machine, you can get 512 gigabytes of memory into a single machine, so why care? Well, as probably every single speaker of the last week has told you, sometimes you have to, because you end up with larger than RAM data sets, and the economics of the problem that you are solving is of the kind where using many machines is very feasible from an economic perspective. If you train the advertisement system for Yahoo, it doesn't matter how many machines you burn in the process, because every little tick in precision uptake will give you some money in return. And of course, streaming the data from disk will help you to some extent doing that. And one fairly successful example of that is John Langford's Whirlpool Wabbit, that streams the data from disk over and over again in a very efficient way, and therefore can allow you to learn from larger than RAM data sets. Also, efficient data structures will help. So for example, if you take the now tiny Netflix data set, and most people represented each individual entry there as a double, which is 8 bytes. But it's only a number between 1 and 5 stars, so why waste 8 bytes on that? So you can get away with a single byte. Tricks like that help you, but ultimately you might hit a data set that's too big and where the performance from disk is not good enough, so you want to go to multiple machines. The other problem, obviously, is if your model is larger than RAM, then streaming from disk is really impractical, because often you have random access to the elements of your model. Think of a matrix factorization problem where you need to update individual entries. So streaming from disk is no longer an option. If you hit models that are bigger than memory, you have to go onto multiple machines. And of course, if you happen to have a computation that is very expensive and you need all the CPU power you can get, then you also will find yourself in a situation where going onto multiple machines is beneficial. So if you think about, Quark was here last week and talked about deep learning. Their paper at NIPS about the deep net image classifier used 1,000 machines to learn 1 billion parameters. 1 billion sounds huge, but think of it in data size. If each of those is a float, you end up with 4 gigabytes of memory used. Yet they used 1,000 computers to do it. Why? Right? The reason is more CPUs help in this case because the problem is fundamentally CPU and not I/O bound. Okay, but what about all these many more smaller data sets out there in the world? The vast majority of data sets easily are in the range of 0 to half a terabyte, so you can load them into main memory. The vast array of models that is out there is way smaller than half a terabyte, so you should be able to do things in main memory. Why should you care about distributed learning in those settings? Well, first of all, it might be all the computer you have, right? When you join any of the internet companies, what you will find is there are clusters of commodity machines. And commodity by now also means like triple-digit gigabytes of memory, but still, you have these clusters that are designed to be multi-use such that they are affordable, right? So you have other frameworks that also need to run there beyond machine learning, let's say billing, and you want to make these clusters as multi-use as they can be. The other aspect that comes into play, especially if you talk about systems like MapReduce and Scope and now Hive, that all produce data, they produce the data already pre-partitioned. And I'm going to go over the details of what that means. So your data is fundamentally already distributed. So in order to run it on a single machine, you have to reunite it on that single machine first. Lastly, the machines in those clusters, they are not purpose-built for machine learning. Right? As much as we like the machine with half a terabyte of memory and 4 GPUs, that's not what you will find in 1,000 copies in a data center. What you will find is some sort of a trade-off between all the different users of those machines and what is the cost-effective configuration of those machines. So for example, GPUs and CPUs are not chosen by peak performance, but by performance per watt. Because at the end of the day, you have to put electricity into those computers, and you have to cool that electricity away again. So using machines that can give you more performance per watt that they consume is hugely beneficial. And also the other workloads that you typically find on those clusters, they are not CPU bound. They are most often I/O bound. Read a terabyte of data, find that one nugget of information, spit out a megabyte of output. That's a very common query case, right? So, and for that, you don't need much CPU. You need lots and lots of I/O capacity. Just as a point of reference, Yahoo published, or Facebook published their cluster configurations, and they have 12 disks per CPU. So it's all about I/O performance for those. So the CPU-heavy machine learning that we would like to do is often met with machines that are not quite the ones. And going on to multiple machines is of real help here. Okay, so I want to start the kind of main part of the tutorial with going over a very brief history of some recent open source distributed systems for big data processing and what people did to make it better and kind of where we are today. So, who has used Hadoop in the audience? Just about anyone. Who liked the experience for machine learning? You will like my next slides. Okay, just for those who didn't raise their hand, Hadoop in version 1 came in with 2 components. HDFS is a distributed file system that has some centralized name node, which you can think of as a database that keeps track of where which file is. The files themselves are chunked into blocks. So if you have a gigabyte of file, that typically ends up being 4 blocks, each 256 megabytes in size. And then in Hadoop 1, each of those blocks would be stored 3 times on different machines. So if you lost the machine, you still had 2 to pick them up from. If you had a disk error on one of the machines, you still could form a majority. MapReduce then was the way in which you could write applications for that cluster. In MapReduce, what you give to the cluster for execution is something very simple. You specify some input folder or files in HDFS. You specify a map function that is applied to each of the records in the dataset. And it spits out key value pairs, let's say a word and whether or not it was found in spam. whether or not it was found in a document that was representing spam and emails. And then you have a reduce function, which gets for every key, in this case the word, all the values, in this case the count in how many documents it was, and reduces this. And just assume you sum them up. If you do all of this and then write it to disk, you have built yourself a naive-based classifier for spam, right? Because you just count words. Now this is super nice if you have algorithms of this kind, right? Because MapReduce does all the heavy lifting for you. It figures out on which machines to run. It figures out when an individual mapper fails, just to rerun that part of the computation. It solves all this sorting out the data in between map and reduce. So the mappers put out key value pairs. They need to be shuffled or sorted to go to the right reducers. All of that is being taken care of, and it's super nice. At that level, it is super nice. So a lot of people came up with the idea of doing distributed learning on MapReduce, or more specifically Hadoop. This is generally a good idea because MapReduce as a logical programming model fits what's known as the statistical query model really well. And in the statistical query model, you express your algorithm as queries against your data set, which produce you statistics of that data set. Think of gradient descent as another example in naive Bayes. You compute the gradient on every data point, and you want to have an aggregate statistics of that. So the map function would compute gradients, the reduce function would sum them up, and a counter, and then as the output, as a very last step, you divide by the counter to get the average gradient. So this sort of thing is very natural on MapReduce. That's why there's a ton of papers. There have been whole systems built around this idea. The open source one would be Mahout, who built machine learning algorithms around that insight. What they've all, without failure, have eventually discovered is that it's not such a great idea on Hadoop version 1. Because Hadoop MapReduce did not support, or still does not support, but there are better options now, does not support iterations. So each time you submit one of these MapReduce jobs, it is exactly load some data, apply the map function, shuffle the data around, run the reduce function, store it on disk. Now, if you have an algorithm that needs 100 iterations to converge, you load the data 100 times from disk, you apply the map function 100 times, you have to do that anyhow, then the mappers write their output data to disk, where it is shuffled, and the reducers eventually do the same. So you have a lot of disk involvement that is the same in each and every of the iterations. Even worse, you have the scheduling overhead. If you have a large cluster, a couple of thousand computers with tens of thousands of CPUs, and you walk up to one of them and you say, here's my job, please run it. The one poor machine in Hadoop 1 that would have to figure out where to run your job would become the bottleneck, and you would sit there for like 10, 20, 30 seconds before your MapReduce job starts. Now think about an algorithm with 100 iterations and half a minute lag before anything starts and a minute of overhead in each iteration. That quickly becomes infeasible in practice. Now there's of course the completely opposite problem where MapReduce is a bad model for computation. And that's for all these graph-based algorithms where you have to send very small amounts of data in between different nodes in your graph computation. That's where MapReduce is just not the right logical model. But even where it is the right logical model, you run into all these issues of overheads. So what have the bright people at Yahoo and otherwise done at the time to help themselves? Well, we built map-only jobs. What we did is we wrote a map job that didn't have a reduce phase, and we blatantly lied to the underlying system. Instead of actually computing a map function on a record, we used that first map call to hijack the machine and run our own computation. So the first map call would give us some control over a process on the machine. Then we instantiate a learning algorithm with, for example, MPI as the communication primitive, and then run in the map machines and eventually releasing the mappers when we are done. So I like to call that Hadoop abuse. We organized a workshop back at Yahoo about this where we said, let's bring the Hadoop team and the Hadoop app users into a room, segregated by a nice line in the middle, and have us talk about this, right? Because this solution is clearly not good to lie to the system. At the same time, it's the only thing we could do given the clusters that we have. I want to first talk a little bit about the kinds of abuse that people did, and then I want to talk about where the industry as a whole is moving to avoid this sort of situation. So let's talk about one kind of Hadoop abuse that was super prevalent and is kind of in decline now because better opportunities are out there. Think about the situation where these P's are your data partitions, and then you have some additional computational nodes that you obtained. Then you send some statistics up that tree and provide new model updates down. Gradient descent would be a good example for an algorithm that you can implement in this way. There's a couple of abuse papers out there, the first of which is the Decision Trees on Hadoop paper by Jerry E. He actually tried implementing it in MapReduce, and in the paper makes a really nice case why that is a bad idea, and then runs an open MPI job as a map-only job on Hadoop instead and obtains great performance gains in this. The other very popular solution in this space is VW from John Langford and al. What they do is they realize that this is the only computational operation that they need in terms of a communications pattern. Aggregate some data, redistribute it to everyone. This is an MPI known as allReduce, and they made a version of this primitive for Hadoop. So what they do is they set up a custom server on the cluster that helps them set up the computation where every of the mappers checks in. Because that's a crucial problem, right? You have your mapper running, but Hadoop didn't tell you on which machine it was running. So the first thing that your map task will have to do is check in with some known location and say, hey, I'm here and I'm ready to compute. So they have their own server for this, where Jerry still used HDFS for the same purpose. And then Worpel Verbit goes ahead, builds a binary aggregation tree, and commences in the execution. They did a really interesting additional trick, and that is, we'll come back to that at a later time, but some of the machines are always slow. For those of you who have run Hadoop MapReduce jobs, that's the curse of the last reducer. You sit there and you wait for the last reducer to finish. If only that thing was done, your day-long job would finally be done. It's very well known that some machines, they go bad and then they are slow instead of broken, and you just sit there and wait. In order to avoid this in an iterative computation, what they did in VW is they run the first iteration on more than the necessary machines using Hadoop's speculative execution, which is designed to conquer this and run some mappers on more than one machine. And then they just used the first one that completed the first iteration, following the insight that if it is fast in the first iteration, it will stay fast. Turns out that that is actually true and it works really well. Lastly, I also contributed to this kind of abuse. We took this kind of to new heights by declaring a new programming model on top of it. We said, okay, what we really want to do is we have some workers that compute on data. Then we aggregate data into one place where we perform an update. Think about the workers computing gradients, the aggregate summing things up, and the update function performing a decision as to how far the step size shall be and all that. In this case, the good news about that approach that we took is we didn't abuse the file system for synchronization anymore. We had kind of better ways with Zookeeper. Okay, the other kind of abuse that people have built on top of Hadoop to kind of avoid the inherent trickiness of writing things in MapReduce that are fast is if you take the graph view where your data and your model are partitioned, so for example, all these cases where the model is really big, and then you want to do message passing in between these graphs. Given that this is at CMU, a very good example of that would be GraphLab. Right? On top of Hadoop as map-only jobs, I'm aware of two systems that do this. Number one is Apache Giraffe. Started at Yahoo, is now at, most of the developers are at Facebook. They built a graph processing framework on top of Hadoop MapReduce, where each of the nodes gets some input in each iteration, computes new output, and in between the iterations that get shuffled to other nodes in the graph. But crucially, for the purpose of this argument is, they still did this by building map-only jobs. The other example is the Yahoo LDA implementation that Alex has worked on, and Shravan, the coworker of mine who worked on the summer school with me. They also instantiate a graphical model as a map-only job use HDFS for synchronization, and do all the things that are necessary to make this sort of thing go fast on Hadoop, which in essence meant lie to the scheduler wherever you can. Okay, so why am I telling you this? Because there are problems with this approach, and the problems come in two flavors. One problem is problems for the abusers, right? The other one is problems for the cluster. Let's talk about the abuser first. First of all, there is a fault tolerance mismatch here. If you are running in a Hadoop cluster and one of your mappers fails, the same thing for MapReduce is to take the work that that machine was supposed to do and put it onto another machine. Now, you don't actually have a mapper anymore. You don't know whether this sort of operation is safe for what's actually going on in those mappers. And just about any of the frameworks that I mentioned, with the exception of Giraffe, don't deal with failure because of it. Not because Hadoop wouldn't detect it or anything, but because it's so awkward to deal with the policy that is in Hadoop that would solve it for you when you're not actually writing a MapReduce job. The other problem that arises is that there's a resource model mismatch. In MapReduce, you would assume that it's a good idea to execute the mapper on a machine that holds the input data. So instead of taking the 256 megabytes of this block that you want to compute on and shuffling that through the network to a machine that runs your map code, you instead take the 20 kilobytes of your map function, send that to the machine that has the data, and compute it there. That makes perfect sense for MapReduce. It makes absolutely no sense whatsoever if what you're doing is load that data into main memory and then communicate a lot with all the other machines. Because for that scenario, you would want to be close to each other in a network sense. So in traditional data centers, that would mean being on the same rack with all of your mappers. That's not a consideration that makes any sense for MapReduce, but makes every sense for these iterative computations. So you're in this awkward mismatch situation again. And lastly, it's a lot of work to write any of these systems, because in addition to having to solve the systems problem, which includes building up networking, figuring out cluster membership, whether or not machines are still there, doing all the data transfers that are necessary, you also have to figure out creative ways of lying to the scheduler. So your problem didn't get easier, but harder. On the other side of this, there are a lot of problems for the cluster. And the biggest one of those is those kinds of abuse scenarios of Hadoop violate the MapReduce assumptions. So for example, if you have a map function, you could assume some sort of proportionality between input and output. If it reads 100 gigabytes, it will produce 10 gigabytes. Okay, if I send it 200 gigabytes, it will produce 20 gigabytes. So I can use that as the scheduler to make optimization decisions. Different from that, these MapReduce jobs that aren't actually MapReduce jobs, they load nothing, then compute really, really long, and then produce some output. And while they are computing, they are hitting local resources, like the local disk. So if you have these bursts of local disk use, and you don't know what's going on, it's a reasonable choice by the cluster management system to say, this hard disk must be broken. Because from the perspective of other jobs, it's sometimes slow. Because the cluster has no clue that what you're actually doing is using a different computational framework. The other situation that arises is if you are in a shared cluster. This kind of abuse is very disrespectful to other users. Because you're violating all sorts of scheduling assumptions of the underlying system, you might make someone else's last reducer slow by doing so. Right? So in exchange for your job being done quickly, someone else sits there and bites their nails and wonders, oh my gosh, I have a paper deadline, it's not done yet. Right? So this is not a good situation to be in. At this point, I want to kind of do a little side note of how I like to think about clusters and clouds. So if you have a cluster, like the kind that you would find in a typical research department, there is almost exclusive ownership. Right? A research group has bought it, they get to use it, they have some kind of armchair or whiteboard scheduling as to when who gets to use all of the cluster, because in order to write the paper, you have to run on all of the nodes at once to get that nice scale figure at the end of the paper. So there is some exclusive use. In that sense, idle time is bad, because you already heckled your coworkers into getting the cluster for this week, And every single minute that not all of the CPUs are doing work is a bad situation for you, because you already, quote unquote, paid for it. The cluster is also unelastic. You have these 100 machines, and unless you write a new grant proposal and get some more machines, it's not going to get bigger anytime soon, or smaller, or anything like that. Smaller maybe if things fail and you don't have budget to replace them. So the optimization goal then for your work is the wall clock time to a solution. If you build a distributed learning algorithm, the only optimization criterion you care about is how fast does it run? Does it run on more CPUs faster than on less? And even if one more CPU brings me a millisecond of speed improvement, I will do it because I already paid for that CPU. Right? There's no other incentive in this game than to use the machines as much as you can for as long as you can till you're kicked off and get as many jobs through in that time. The cloud, on the other hand, is rented on a per resource basis. Think of the most basic cloud. When you go up there, you rent virtual machines. You pay for them either in hour increments on some clouds or in minute increments. But at the end of the day, you pay for it. You pay for it by usage. So there is a very strong incentive to actually have idle times as long as you switch off your resource usage during that time, because you don't pay for it when you're not using it, different from the cluster that you have in your basement. And you can write elastic applications. You can decide at runtime of your application to just add some more CPUs or to remove some or stuff like that. So there's a real chance here. So the optimization goals become much more interesting. I won't have time to talk about the implications of that for machine learning, but if you think about it, you could think of the cheapest way to compute a model given a deadline. This is a very common scenario. Sunday morning, 5 a.m., you need the new advertisement model, and you have the input data at 2 a.m. What do? Do you rush on 1,000 computers to have it done by 2:15, or do you kind of do a leisurely pace where you might incur less cost? Another problem, optimization goal could be you want the fastest path that you can get within a given budget. It's kind of a variant of the cluster situation. Okay, for both the cloud and for this problem of MapReduce app use, the industry is converging on what's known as resource managers. So resource managers, there's a couple of them coming up in the literature in the last 2 or 3 years. The first of which was Apache Mesos coming out of Berkeley. Then Google wrote a paper on theirs, on Omega. And then there's Apache Yarn, which is the resource manager that's part of Hadoop 2. So whenever you get to a Hadoop 2 cluster, you can assume that MapReduce is not your only option. What your other option is, I'm going to talk about for the rest of the tutorial. So these resource managers vary greatly in how you get resources, but they don't vary in what it is that they actually manage, right? Because I said resource managers, but what is a resource and how is it managed? So they generally view the whole cluster as a collection of containers. They can have varying sizes. I'm just going to use this kind of grid visualization for the rest of this tutorial, where each of those containers is a slice of a computer. Think of it as some amount of memory, some amount of CPU, some amount of networking, some amount of disk. It's a reservation for resource utilization on an individual computer. So why is this cool? You can now walk up to this resource manager and say, give me 5 gigabyte containers with 2 CPUs each. And someone else walks up, no, my resource utilization is of the form, I want 1 container with 64 gigabytes of memory and 2 CPUs or 5 CPUs. So we now can enable what's known as multitenancy or even true multitenancy. On the same cluster, you can run many, many different workloads and negotiate in between them. For example, you could have a streaming job sitting there that needs to satisfy some latency constraints that you have, right? You have a click on a website and that needs to be represented in the front page advertisement module within 2 minutes. So that guy has certain resource requirements. Another one might be a batch job that needs to be done within the next 5 hours, but who cares when within this window, right? Yet another one might be an interactive session where someone would be really upset if it all of a sudden would go slow. But also what this enables is, or shall enable, I should say, is that you have many, many different users of the same hardware sharing it under some sort of resource governance. By all of them having to go through the resource manager to get them, you get billing, and you get separation between the users. But it's tricky to write applications in this world, and I'm going to try to visualize that in a couple of slides. So think about a job that sits there in these blue containers. Do they actually come across? Yes, they do. You have your job sitting there in 5 containers, and it's running, and it's doing some, let's say, MPI-based message passing algorithm for a graphical model. Now disaster strikes. Some of the machines disappear, right? So you need to deal with that somehow, right? One perfectly fine way is to crash and restart. That's what a lot of people argue for if their system is fast enough. Then there might be another situation where someone else is more important on this cluster at that time and takes away machines from you. This might look to you just like a crash because the machine is taken away from you. But another situation might be that you get told up front that this will happen in, let's say, half a minute, so you better vacate those machines. So that's the difference between hard and soft preemption. Hard preemption is your machine goes away. Soft preemption is you get told to please vacate some machines. If you fail to do so, soft preemption turns into hard preemption and looks like a failure to you. Lastly, you might be the lucky job, right? So some resources just became available, and the resource manager makes it known to you that if you wanted 10 instead of 5 containers, you can have them. Now, how do you make the decision whether that's a worthwhile endeavor? Right? You might be at the end of your optimization anyhow, and reshuffling the data onto 10 machines might take longer than what you would gain. So it's not obvious what to do in these situations. I'm going to illustrate it with a couple of examples, kind of the classical examples. If you write a MapReduce engine, think about of yourself as the person who implements MapReduce. They have to consider the situation where failure occurs. And the very traditional way they do it is they just write things to disk. Right? That's why MapReduce is so disk intensive. Everything that has been computed gets written to disk, such that if the computer that computed it goes away, it doesn't matter. The other situation that you typically have in MapReduce is you only know how much data you have for the reducers when the mappers have run. So at that very moment, you need to decide how many reducers you want to schedule, and you might find yourself with wrong assumptions from initial. You might find yourself in a situation where you initially made the wrong assumption. So you need to scale up, right? In those cases, it's kind of known, right? The database literature has been at this for 30 years. They have their answers. In machine learning, we don't. Another example that people care about on these clusters is, of course, machine learning, which, as I was mentioning, MapReduce is a really poor model for iterative computation. So what we want is more like MPI on these clusters, right? So we want to run an iterative computation on this cluster, and we want this to be supported by the underlying infrastructure. And of course, I also already mentioned that you want to do graph processing on these clusters, right? So you have your shared infrastructure, you want to instantiate a graph processing system under all of these stresses that come onto it, right? Machines fail, there's soft and hard preemption, there's the opportunity to scale up. How do you make decisions in this world? So we are, of course, not the first people to talk about this, right, in the Reef project. Lots of people have built engines on top of resource managers in the last 2 years for just about any of those use cases. There are graph processing frameworks, there are iterative MapReduce frameworks, there are SQL engines, what have you. So this is good because now those people all get to share one cluster, right? You no longer have to have that one MapReduce cluster and then lie to it if you want to do something else. You now have a principled way of running on this. But I would argue that it is not quite there yet, because what we now have is silos on the cluster as opposed to on different clusters. Each of those silos is, again, hard to build, right? We have done very little to make the life of the person implementing the graph processing system easier. We have also done very little to make machine learning easier on those clusters outside of not having to lie to the system anymore. And in practice, those silos form pipelines. So if you think about last week's tutorial with the parameter server, the data that you run the algorithm on needs to be processed by something. It needs to be generated by something. And if it's not a well-known data set that you go to a website and download, you're probably the one who does that. And if it's fresh data every day, you better have that working in kind of a repeatable fashion such that you can train new models on a predictable schedule. So in practice, what you will find is there is some sort of SQL or MapReduce-like processing going on that feeds into your machine learning algorithm. Now, if you have these different silos, this is really inconvenient because each of them has different failure scenarios, each of them has a different configuration mechanism, each of them will have to schedule containers on their own decision boundary and all that. It's really tricky. So this is where Reef comes in, where we try to build the next layer on a resource manager that is still broadly applicable to all the different use cases. And the way that I found successful in thinking about Reef is if the resource manager and the distributed file system form something like a cluster or cloud operating system, then you can think of Reef as the standard library. Just like on your laptop, you have applications ranging from database servers over compilers to Photoshop. They all need a memory allocator. They all need to open files. They all need to connect to the network. At least I hope so. So what we try to do with Reef, we try to be broad in appeal. That means that we favor mechanisms over policies. What do I mean by mechanism and policy? A mechanism in fault tolerance, for example, would detect the failure and provide options. If a machine fails, Reef will detect that and tell your application, but then it's up to your application what you want to do with that knowledge. Do you, for example, want to crash because you can't tolerate failure? Or do you, for example, want to figure out what ran on this machine and send it to another one? Right? MapReduce, on the other hand, couples a mechanism with a policy. The mechanism there is the same. It detects that the machine failed. But there's also a policy, and the policy is run on another machine again. What if you don't want that? Then you have to lie again, and we are in all that business again. The other goal that we have with Reef is to avoid silos. We will touch that a very little bit during this tutorial. But the core insight is that we recognize the need for these different frameworks. Right? You have lots. The systems literature is full of papers that suggest the one system to rule them all. If only everything was written in MapReduce, then we wouldn't have this problem, right? If only everything was written in SQL, then we wouldn't have this problem and Oracle would solve it for us, right? In reality, that doesn't seem to stick, that sort of notion. Because new applications come up in machine learning, new ways to compute things come up. So it's not going to stick anytime soon. So what we try to do is, what is the kind of highest layer we can build that is broadly applicable and still allows this handover? So a question that we ask ourselves is, if the data comes from MapReduce and the computation happens in MPI, how can we make that efficient? Right? Lastly, for those of you who have used MapReduce and Hadoop, it's incredibly painful and comes with a high performance hit if you do anything but Java development. Because it's just not meant to be anything but Java. So we did some work in Reef to make that a little easier. It will be not applicable to this tutorial where we do everything in Java. But if you have C code that you want to kind of distribute on a Hadoop cluster, Reef can help. Okay, so I told you a little bit about why we did Reef, what it tries to accomplish, and all that. Now I want to tell you about how a typical Reef application actually lays out in time. So as I was mentioning, we assume that there is some sort of resource manager in the cluster. As it's called yarn, it's this big ball of yarn in the upper right corner. And we assume yarn to deal with all the resource governance. So when you submit a job and you actually don't have a user account there, that's yarn's problem, not ours, right? To tell you that you need to go to another cluster. Then per job, so per application or per algorithm or whatever you want to run on the cluster, we have the notion of a job driver. That's the master of your computation. It deals with all sorts of control flow decisions. For example, what to do when it starts up, what to do when a task fails on a machine, all that sort of thing. It also needs to figure out when it's done, right? Because at some point you need to exit your program. In this case, the driver goes ahead and asks for 3 containers that are on those machines which already have some data, and 3 more. And because this is a good day on the cluster, we immediately get exactly what we asked for. This might not be the case when you run on an actual yarn cluster, because those resources might not be available for you at that time. So what we then instantiate in those containers that we get back from the resource manager is evaluators. An evaluator is a process that sits there idly waiting for commands. That's how you can think about it. The evaluators crucially outlive anything that you ask them to do. So if you send a task to them, in this case 2 different tasks on 6 machines total, and they can then execute in the evaluator. Now, of course, as I was mentioning earlier, disaster strikes once in a while, and a machine disappears, or a container disappears, typically in the form of a whole machine disappearing. In that case, we fire an event to your driver, and the driver then has options on what to do, right? It has to figure out, hey, I lost a machine. Do I do anything about it? And if so, what? In this case, the driver wants to reinstantiate its computation, goes to the resource manager, asks for a new evaluator. Luckily, it gets it and instantiates the computation in that. Right? Again, the decision what to do in this case was the application's decision. Reef didn't make that call. Reef made it easy and very obvious that you have to make that call, but it didn't decide. Now, of course, tasks are done at some point, in which case the evaluators stick around. This will be very crucial later in the talk, where you can think of the first task is the one that loads data into main memory, and then it is in the main memory of the evaluator, and then the second task actually computes with it. That helps with this whole handover between different frameworks. You can think of MapReduce loading your data into main memory, and then you send your MPI program to those computers. Okay, in this case, we just sent something else there. Okay, so why is this retaining of evaluators cool? So there are a couple of use cases why we think it's useful, and we have yet to find some more. If you have a MapReduce job, so often when you do machine learning, you want your data partitioned in some convenient sizes. Let's say your maximum container size is 16 gigabytes. Then you want to have your terabyte data set split into 16 gigabyte blocks. Right? It's very convenient to do in MapReduce. You just assign to each record that you read a number between 0 and 15. You're done. Right? And you set the number of reducers to 16. Now you have files. Now you have to schedule yet another job that loads it and runs with it. What you can do with Reef is you can run the MapReduce job and then just change out the task on the reducers from the task that used to do the reduce to a task that computes with it with your algorithm. Now, and then, of course, we can set up some sort of iterative computation because the machines outlive any particular task. Right? We can send a task, wait for its completion, decide what to do next, and send the next task again if you have a purely iterative computation. Lastly, it's useful, we haven't built anything that uses that yet, for interactive queries, where you load some data into main memory on a couple of machines, and then you just keep submitting code to that data from an interactive prompt. For those of you who are familiar with Spark, that's pretty much how that would look like. Okay, so I walked you through a control flow in Reef, and don't worry, we will do this much slower and with gory details in code again. But what I want you to take away from this is, it seems like a lot of work compared to writing a MapReduce job, but it's actually much easier than not having Reef. Because what Reef does for you, it centralizes all the control flow decisions. So, for example, if an evaluator crashes at the other end of your cluster, Reef's default behavior is to crash your job. That sounds like not much. But why on earth should your driver crash just because something else in another virtual machine threw an exception? Right? That's a feature, not a bug. It's really hard to accept, but that's the case. We also centralize all the error handling. When anything in an evaluator throws an exception, division by 0, out of memory, anything of that kind, and the code, the task that you submitted to that evaluator doesn't catch it, we will catch it, send that exception to the driver, and present it there. The most useful case for that is the out-of-memory situation. When a task runs out of memory, that's typically because you didn't ask for a large enough container for it. So in this case, the task can do nothing about it, right? It's limited by the container that it has. But the driver can go ahead and ask for another container that's bigger and reinstantiate the computation there. This design is also fairly scalable because in the driver, everything is event-based. This goes down to the point of there is no entry method. You get an event that your driver can now start, and that's when your application starts. This allows us to schedule these events on as many threads and CPUs as we find in that machine where your driver happens to run. So this is fairly scalable as long as you don't write blocking event handlers. And it should scale easily to thousands of containers. Also, the Reef design is mostly stateless. So the driver itself keeps almost no data. That is important if you consider the case that the driver itself fails. So just like any other evaluator or container, the machine that the driver runs on can fail. And then you need to restart. And if the driver has gigabytes and gigabytes of state that it needs to continuously maintain on disk such that this restart can happen, that would be a bad situation. So Reef is in itself as stateless as we could make it. Then, of course, if your application has gigabytes and gigabytes of state in the driver, then, well, we can't do much about that. You'll hear me talk also about two support libraries in Reef that we built for Reef. Wake is that layer that makes this event-based programming possible for us and that sends the events across the network and all that. We will only touch that very, very thinly by implementing a couple of interfaces, but it's not something that you need to consider yourself with during this tutorial. The other thing that we built, and that's actually fairly crucial for the tutorial, is Tang. And I wanted today give you kind of the feature, what it does, and then later in the week, how it's used and how it does what it does. So for those of you who have written distributed systems or have used Hadoop, how many of you have run a job purely to see whether you misspelled a parameter? A few. The other ones are too modest to say yes to this question. Yeah, because configuring distributed systems is incredibly hard. The driver makes some decision about how the configuration should be for a task executing somewhere else. It sets paths, it sets memory sizes, it sets all of this, right? And then the Hadoop team has the great idea of renaming the memory size of a mapper, right? The parameter for this. You misspell it, it goes unnoticed till you run out of memory, right? So this is bad, and it's hard. So what we said is, okay, let's do something about it. Even though it's not, as machine learning people and systems people, not on the first on the list that you want to write a paper about, configuration systems. But hey, let's do something about it. We should get into a better state. So we view configuration as dependency injection, which enables early and static checks of your configuration. So I want to show this in kind of a feature form today, and probably tomorrow we'll get to how it's actually used in practice. So what you might find on a Hadoop cluster when you say, let's say you have a map task that spawns another process that shall execute ls in this case. A very common exception that you might find is some sort of null pointer exception because you accessed an entry in the configuration that wasn't actually there. Default behavior is to return you a null. Then you pass that on to another method in your program which will throw the null pointer exception. And now you sit there trying to figure out what on earth went wrong and why did I have to sit here for a minute to get that error message out of my task, right? So what if you could instead get this? Some system tells you there's an unknown parameter called command that no one asked for, but it's in the configuration nonetheless. There's a required parameter called CMD that isn't set. It's the typical rename situation, right? Tang makes this sort of this sort of error message possible. And in many, many cases, we are there in terms of being this crisp. Okay, so now we fix this. Now we have a task that depends on this information, but we bind that task to another parameter that expects an evaluator, right? So this is a typical type error in your configuration, and then it would just tell you, hey, you gave me the wrong kind. In this case, we fix it the other way around by actually asking for a task. And then if you think this through till the very end, you get kind of a dependency graph of objects. In order to instantiate an evaluator, you need to know which instance. Well, the yarn evaluator. The yarn evaluator in itself depends on a task. Which instance? Well, the shell task. The shell task has a parameter called CMD, which needs to be bound, in this case to ls. If anything in this dependency graph is not correct, we can tell you at very early times. If you misspelled in the compiler, if you miss required parameters, then we have static analysis for that. If you submit a task to an evaluator that doesn't actually have an object that you require, we tell you before you submit the task, tells you already on the driver. So this saves hours and hours of debug time. I cannot overstate how much this sort of thing helps. And for those of you who have tried to write distributed applications, this is very obvious. For those of you who haven't, you just sit there saying, what is he talking about? It's easy, right? You set a key value store. I'll get back to that easy part. Okay, this was all about control plane, and this is kind of utterly boring because at the end of the day, we want to do something with data, right? We have some data on disk, we want to do some computation on it. So in Reef, we are working on a couple of data primitives. One of them is fault-tolerant communication. If you have two tasks talking to each other, and you must assume that one of them might disappear at some point, then you have some ways of dealing with this. Number one is you have some sort of name service that keeps track of where is which task when, assuming that it will be reinstantiated. Right? The other one is you have a mailbox. You don't have direct communication in between tasks, but one task sends to the mailbox of the other, and when the other eventually comes online, it fetches it. Then something that we will do a lot of work with during this tutorial is group communication. And by that we mean what the MPI standard calls collective communications. So for those of you who have written MPI programs, that's stuff like broadcast, reduce, or reduce, scatter, gather, and all that. But none of the MPI primitives apply directly to this world, because the MPI standard is very strict about the fact that the number of participants of your computation cannot change at runtime. Right? While your application is running, if you're writing an MPI program, you can't add or remove nodes. This totally doesn't fly in this world, because you might be offered 100 machines for free. For sure you want to add them to your computation. And lastly, we have some low latency communication libraries that just are not fault tolerant, but instead are low latency in between two nodes for those cases where you have a graph computation where you send small messages a lot. We also have storage and checkpointing. We will not touch much of that during this tutorial. Okay, coming to an end of the first hour, I hope I instilled on you that resource management is upon us. There's really no way to write distributed applications for the predominant big data platforms, which would be Hadoop and its variants, without considering resource management underneath. Just as an additional point, if you think about the two biggest cloud operators right now, Amazon has spot pricing for their virtual machines. So the price goes up and down based on how much demand there is. Azure, on the other hand, bills by the minute and doesn't have spot pricing instead of hours. So at Amazon you pay for the hour, at Microsoft you pay for the minute. Now just imagine a world where these two good ideas cross, where you're sitting on computational resources that change price once a minute, or ideally more often, right? Because you want a more perfect market for this. Now you're sitting there computing gradients or passing messages or whatever on 100 machines, and the number of and the price just doubled. What do? Do you kind of shut down half of your machines, or do you hope that you converge fast enough, or what do? Those sorts of questions will come up on the public cloud as a utility. They don't right now because these two thought streams haven't crossed yet, but I'm pretty sure that it will happen. I believe, and I have to, right, because I invested 2 years of my life into it, is that Reef provides a useful abstraction in this world, where it's not too high to be useless for many applications, but very useful for only a few. It's also not too low in the sense that it doesn't help you anything. It doesn't help in principle. It does not take away any principled problem of writing a distributed program. It just makes every principled problem of writing a distributed program practically very accessible. So when a machine fails, we tell you, you don't have to figure that out. When a task is done, we tell you, you don't have to figure that out. When you have a resource allocation that's satisfied, we tell you, you don't have to figure that out. But what to do with that information, kind of the hard part of building distributed algorithms, nothing of that kind is in Reef at this point. And it shouldn't, because it should have broad appeal. So I had this title about resource-aware machine learning. And I'm going to just postulate that that looks like a promising idea. And I've told you nothing about it, but as always in talks, I'm just going to demonstrate it by graph. In this case, I conveniently left out, no, not most of the information. But if you think about running on a cluster or a cloud, and you require 254 partitions of data to be loaded. So a very naive way, and you run gradient descent. This is a variant of gradient descent run on the gene expression data set that Langford et al. Used in the terascale learning paper. A very naive way would be to go to your resource manager, ask for 254 machines. When they are all there, you ask them all to load the data into main memory. When they're all done with that, you commence your all reduce operations. That is the red line. So you wait for a long while, in this case on a loaded cluster, 10 minutes. Then you wait a little more to load the data, and then you see the learning curve that you would expect. Now, okay, this cluster might be terrible, and you had to wait for 10 minutes even for the allocation. So what if you would subtract the whole allocation time from this and had an ideal cluster that is all to yourself? You just go there, you ask for 254, you get them immediately. That's the green line. The green line is a lot better, obviously, but it's still pretty bad because you still have to wait for the slowest of the machines to load the data before you can either enter the first iteration or exit it. At one of these 2 points, you have a barrier where all of the machines have to have checked in. And as I was saying when I referred to the one slow reducer, this can actually happen, right? You can have situations where machines are slow. Lastly, the blue line is something that we call ramp up. In this case, we say, well, there are all these lovely papers that say that you should do some learning on a subset of your data, and once some statistical condition of your model is met, add some more data and continue. You just say, okay, what if we replace the statistical condition with the system and just run on, let's say, 4 machines, one iteration, and whatever machine became available in between takes part in the next iteration and so on. So in this case, the first iteration actually only runs on 2 or 3 actual partitions of the data that we had at the time rather immediately. And then, of course, as you would expect, in the beginning of your optimization, it doesn't matter that much that you have a lot of data. So and we can do much, much faster. And I would call a graph where a quote-unquote promising approach is done before the current state-of-the-art can start very promising. Okay, there are a couple of developments by others on Reef that I wanted to highlight towards the end of today. One is Surf. That's done by Seoul National University and SK Telecom. They built an in-memory file system in Reef because memory is getting cheaper. The data sets are also getting bigger, but the important ones often don't. So keeping things in main memory is an interesting approach. Grouper is kind of a generalization of the MPI primitives and what you would call a shuffle phase in Hadoop. How can you make this more general? Because whether you do an MPI reduce or a MapReduce job, it looks a lot alike from some angle. A quick statement on the status of the project. The code has been released on GitHub. It's Apache 2 license, so that should give no one who works for a company in the audience trouble using it, touching it, and all that. We do time-based releases. That means on the 21st of each month there is a release. The very fact that I'm here this week means that the release on the 21st of this month will be a little less in volume than others, because we don't say the following features are a release. We just make one on the 21st. We are currently on version 0.5. For the summer school, we will use version 0.6 snapshot. We tried it on all the various Hadoop distributions we could find. That's it for today, and I think I'm perfectly on time. Thanks. Questions? Yeah.
Why did you keep the decision to use Java as a language?
Why did we keep the decision to use Java as a language? It's easy to integrate into the both technical and social community around Hadoop.
Okay, well, just because it's Hadoop-based.
Yes. Yeah.
How does this compare with Spark?
How does this compare with Spark? This is the most asked question. So if you think about, if you had Reef, building Spark would be easy. The other way around, not. So Reef occupies an ever so slightly lower layer in the stack of big data tools. So if you think about how would you implement a parameter server in Spark, the answer will be some sort of lying to the underlying system. If you would say how to build a parameter server in Reef, I would say come talk to me. I would love for someone to do it. Right? It's very straightforward to do. Okay. Yeah.
Do you run anything else than Yarn?
Yes, we do. We have, and you will come in touch with that, if we are unlucky for all of the summer school, the local runtime, which just simulates containers on your local process. We have some networking issues to our cluster from here, which is a bit unfortunate. So we have a local runtime that's pretty awesome for debugging because you just run locally. You can just connect with the debugger to your containers and just talk to them. Then the guys in Korea are working on a port of Reef to Mesos, which is the other open source resource manager. There's nothing in principle that stops Reef to be ported to any resource manager. As a matter of fact, we have that as an abstraction layer in the software because that's one of the value props of Reef, to write it once, and if Yarn wins and you originally set on Mesos, then you're good, and the other way around. So, yeah.
Are there any default policies that you do provide?
Yes, I'll go over them tomorrow, but in general, we try, whenever you don't listen to an event, we either shrink your computation. So if a task is done, we will return the evaluator if you don't do anything. Or if there's a failure, we declare job failure. We try to make your computation cheaper. That's the default policy. Okay. We are 2 minutes over to coffee or something. So let's end.